Now moving on to 19.4, RL circuit analysis and circuit parameters. The phase relationship between conductance, inductive susceptance, or B sub L, and admittance are shown in the diagram. So if we take a look at these diagrams, you can see to the right we've got a diagram that shows the susceptance capacitive and its relationship then to the admittance. If we look to the left here, we have the same sort of diagram, but this diagram is showing us the total current in a capacitor, the total current in the circuit, and our voltage and current through the resistor relationship. Again, like I said before, we've got a current source here. That's what the little circuit with the arrow is showing us. And that's pretty common when we look at parallel circuits. So inductive susceptance then is determined by the equation. Again, this looks a lot like what we saw for X sub C, 2 pi FC, but now since we're dealing with reciprocals, this becomes the reciprocal of the inductive reactance 2 pi FL. So if we take a look at an example here, we have a resistor in the circuit, 6.8 k ohms. We have an inductor in the circuit, 200 millihenries, and an operating frequency of 4K or 4,000 hertz. Our total current being delivered by that current source is 10 milliamps. So they ask us to find Y and I sub T, Y being the admittance. So since we're looking at resolving this down using the reciprocals and those parameters associated with a parallel circuit or parallel network, we're going to start with finding the conductance. So 1 over R, 1 over 6.8 k ohms gives us 147 microsiemens. B sub L, which is our susceptance for an inductor, 1 over 2 pi FL. Plug in our values, we get 199 microsiemens. Everything is in Siemens because we're dealing with the reciprocals. So the admittance then for the rectangular value, 147 microsiemens minus 199 microsiemens. So we can use those two values that we just solved for in our tangent relationship. You'll have to, go back and recall the diagram here, why we're choosing the values that we're choosing here. But the tangent of B sub L over G then gives us minus 1.35. Taking the inverse tangent, then we get minus 53.5 degrees, which is our phase angle. Using the sine of theta is equal to B sub L over Y gives us what we need to solve for Y. So we rearrange the terms, putting the sine theta in the denominator, and we are able to solve for Y equals 247 microsiemens. Okay, so as we take a look at the values here, Y polar should have been 7, not 8. Y polar then is equal to 247 microsiemens at an angle of minus 53.5 degrees. The current polar then is that 10 milliamps that was given at an angle of minus 53.5 degrees. Solving for, as we did before, I sub R is equal to IT cosine theta. We get 5.94 milliamps, and the total current in the inductor, 8.04 milliamps negative. Again, it's not shown here, but we could have calculated I sub R and I sub L using the Ohm's law relationships that we've used in the past. Finally, the rectangular value for the current, 5.94 minus J, 8.084 milliamps. Looking at another problem here, now we're given the resistance value of 12 k ohms, the inductance value of 100 millihenries. We have the phase angle given, minus 40 degrees, and the current through the resistor 50 microamps. So in this case, they want us to use what's given to calculate the operating frequency, Y and I sub t in both forms. So we start with solving for our conductance, 1 over R, since the resistance was given. In a lot of cases, you just start picking things and determine, do you have enough information here to solve for what we are looking for in any particular relationship. So we didn't need that there. B sub L then is equal to G tangent theta. Okay, that's just using the sides of the triangles, and we get minus 69.9 microsiemens. The rectangular relationship then becomes Y rectangular is equal to 83.3 microsiemens, that's from our conductance, minus J 69.9 microsiemens from B sub L. Going back to the cosine theta, G over Y, moving the terms around, G over cosine theta then gives us 109 microsiemens. So at this point we can put together the polar form, 109 microsiemens at an angle of minus 40, which was given as our phase angle. We can now also calculate the operating frequency, 1 over 2 pi B sub L times L. By moving those two values around, B sub L and F, we can calculate 22.8 kilohertz. Again, using the definition for the tangent, I sub L divided by I sub t, moving the terms around, we get a value of 50 microamps times the tangent of minus 40 degrees that was given equals minus 42 microamps of current through the inductor. The rectangular value for the current then for the total current becomes 50 microamps minus J 42 microamps. The total current then is equal to I sub R over the cosine of minus 40, 65.3 microamps, gives us then a total polar relationship for the total current of 65.3 microamps at an angle of minus 40 degrees. So in the next video, we will take a look at equivalent circuits. Are there any ways that we can create relationships with equivalencies of circuits by using phasors? So we'll do that in the next video.